Hello friends, this is Deepak Kumar, Assistant Professor in Kite Group of Institution. In today's session, we will discuss the concept of Prim's algorithm. So in our previous video, I just discussed the concept of Kruskal's algorithm. So we know that whenever we want to find out the minimum spanning tree, so for finding minimum spanning tree, the two algorithms are basically used. The very first one is the Kruskal algorithm and the next one is the Prim's algorithm. In Kruskal algorithm, we just arrange all the edges in ascending or descending order, and then we just select an arbitrary edge having minimum weight and add it in our spanning tree. But in Prim's algorithm, we arbitrarily select any vertex and that vertex will be considered as a root node. So we just understand the concept of Prim's algorithm with the help of this example. So here we have a graph that is your undirected graph and weighted graph, and it is your connected graph also, because we can move from one vertex to another vertex. Why it is weighted? Because here we have weight assigned in a particular edges, so that's why this is your weighted graph, and here there is no direction, so that's why this is known as undirected graph. So we have undirected, connected, weighted graph, and now we want to find out the minimum spanning tree in this particular graph using Prim's algorithm. Now just see how the minimum spanning tree can be find out. The very first step of Prim's algorithm is remove all self loop and parallel edges. So what is self loop? If we have an edge that is starting with a particular vertex and end with that vertex also, so that edge is known as a self loop. So there is no need to consider the weight of this particular edge, because this self loop is removed in this Prim's algorithm. Now we just find out that is there any parallel edges in a particular graph. So if there are parallel edges in a particular graph, then we remove all parallel edges also. So here we have two parallel edges, 9 and 6. Why these are parallel edges? Because when the two vertex have more than two edges, then that edges are known as a parallel edges. There may be a possibility some more parallel edges are available over here, but our aim is to retain the edge having minimum weight. So in this particular case, here we have two parallel edges, but 6 is the minimum weight, so we just retain this 6 and remove this 9. Okay, so after removing self loop and parallel edges, we just find out this particular graph. Now what we do, we just choose any arbitrary vertex as a root vertex. We can choose any vertex in this particular graph as a root vertex and start from there. Why? What is the reason behind that? Why we can choose any vertex? Because we know that we want to find out the spanning tree, and the spanning tree is also a connected. So when we choose any vertex as a root vertex, then there is one edge that is always connected with the remaining trees, because this is your connected. So that's why we can choose any arbitrary vertex as a root vertex. So in this particular case, we just choose this S as a root vertex. After choosing a particular vertex as a root vertex, what we do, we check incident edges on that particular selected vertex and select the edge with least cost. So if we are talking about this starting vertex S, so there are two edges incident on this particular vertex, that is 7 and the next one is your 8. But we choose this 7. Why? Because 7 is minimum in between this 7 and 2. So we just choose this 7. Then we have two vertex. The first one is S and the next one is A. Now we just consider all the incident edges for this vertex S as well as this vertex A. We are not focusing only this particular vertex A. We also consider this vertex S also. So if we are talking about A, so from A we have two incident edge, that is 6 and 3. Actually 7 is already considered, so it is not counted. So we have two incident edge for A, vertex A, that is 6 and 3, and one incident edge for this vertex S, that is 8. So now we just find out the minimum edge of these three edge, that is 6, 3 and 8. So which one is the minimum? This 3 is the minimum edge. Okay. Now we just select this particular edge. Then we have one more vertex, that is C. Now we are not only considering this C, we also consider vertex A and S also. So from vertex S we have one incident edge, that is 8. From vertex A we have, right now we have one incident edge, that is 6. And from vertex C now we have one incident edge, that is 3. So out of these three, 8, 6 and 3, which one is the minimum? This 3 is the minimum. So now this edge will be included in our spanning tree. So we just add this edge in our spanning tree. Whenever we are adding a particular edge, then make sure that the spanning tree property must satisfy. That means there is no cycle in a spanning tree or in any particular tree. So when we add these three edge, then right now we don't have any cycle. Now what we do, right now we have four vertex, vertex S, A, C and D. Now we just consider all the incident edges of these vertex. So for vertex S we have this incident edge, that is 8. For vertex A we have this incident edge remaining, that is 6. For vertex C we have this incident edge that is remaining, and for vertex D we have these two incident edge. So out of this 8, 6, 4, 2 and 2, 2 is actually the minimum. So we have actually two edges having weight 2. So we can choose any one out of these two edges. So now just consider this edge, that is DB. So this edge will be included in our spanning tree, because when we add this particular edge, then right now we don't have any cycles. So this will be included. Now we have total 5 vertex S, A, C, D and B. Now we just consider all the incident edges for these vertex. So S to C we have incident edge 8. Actually we have incident edge 7 also for S, but this 7 is already included. Okay, so we just consider only those incident edges that are not included in MST. So for vertex A we have one incident remaining, that is 6. For vertex C we have one incident edge remaining, that is 4. For vertex B we have one incident edge remaining, that is 5. 6 also, but 6 is covered by A. Now for this D we have one incident edge, that is 2. So out of these incident edge we just find out the minimum weight. So which edge have a minimum weight? That this edge have a minimum weight, that is DT. So now this edge will be included in our spanning tree. So when we add this particular edge in our spanning tree, then finally we have these structures. So right now when we focus on this particular structure, then we see that now it covers all the vertex of our graph. Actually the graph have total 6 vertex. Now all 6 vertex has been covered. And how many edges right now? We have 1, 2, 3, 4 and 5. So 5 edges we have. So if we have 6 vertex and 5 edges, so that is basically a tree. And actually it is calculated by Prim's algorithm. That means that is your minimum spanning tree. When we find out the cost of this particular spanning tree, then this is your minimum cost. So as I earlier told you that there are number of spanning trees are possible for a particular graph, but Prim's and Kruskal algorithm basically find out that spanning tree that have minimum weight. So when we calculate the weight of this spanning tree, so what is the weight of this spanning tree? That is 7 plus 3 plus 3 plus 2 plus 2, that is 17. So that is the minimum weight spanning tree for this particular graph. Actually these two algorithms, that is Prim's algorithm and Kruskal algorithms, are basically a greedy algorithm. Why it is known as greedy algorithm? Because these two algorithms are greedy to find out the minimum weight edge or the minimum cost edge. So that's why these two algorithms are known as greedy algorithm. So that is all about your Prim's algorithm. And in these with the help of these two algorithms, that is Prim's and Kruskal, we just find out the minimum spanning tree for a particular graph. This is all about your minimum spanning tree algorithm. Thank you so much.